So something along these lines. T to the 1/4, excuse me, 1/2. Minus 10t to the 1/4 plus 25 equals 0. So we're going to rewrite it as a quadratic by saying, let's let u be t to the 1/4. Then what you're doing is you're squaring both sides of this. So square this left side, you're going to have u squared. Now, t to the 1/4 all to the power of 2, power rule says multiply the exponents. That is 2 times 1/4, which would be 1/2. And that's exactly what you're looking for. So let u go to the middle. Let u equal that variable to whatever power and square both sides. And what you should end up with is on the leading term, u squared will be exactly that. So you can make the substitutions. You're going to have u squared minus 10 u plus 25 equals 0. So then we'll solve the quadratic. It is factorable. It's going to be a u minus 5 times a u minus 5. Which is u minus 5 all squared equals 0. So if you end up with a perfect square equals 0, all you really need to figure out is what makes u minus 5 equal to 0. You could look at it as taking square root of both sides, and that will get you to here. So in this case, we can isolate u really quick, and we've got u equals 5. Now, but you're looking for solutions, not of u, but for t. So go back to the beginning. I had let u be t to the 1/4. So I'm going to put back in for u, t to the 1/4 equals 5. So at this point, it's how do I undo this to get just t by itself? I would have to raise both sides to a power of 4 in this case. So 1/4 times 4 is 1. So I've isolated t. And then it's 5 to the 4th, which I believe should be 625. Just a quick check of my arithmetic. And that is correct, 625. Questions on that? Good? Okay. And I had also talked with Ms. DeWeese, and always my preference is the test be done in one sitting. And as I said, I did try to make it within your time frame. The original, so the test that you took was actually 5 problems less than the same test that I had my students take, but they have an hour and a half, as you know, so basically double your time. They had 23 problems. I believe yours was 18. So, but if you do go over, I told her just as long as the teachers are okay in your next classes and whatnot, and she's okay with it, you know, just to let you finish it in that setting. So, so anyway, that's how we'll move forward on that. I do believe what we're going to do with chapter 2, which is only 4 sections, we're going to cover 2.2 today with my class, because I want to get to chapter 3. That's really where college algebra starts, with the study of functions. This is really kind of preliminary algebraic stuff we're going to need for functions. Is that next test, since I'm going to allow my class into college to take that like it were a quiz, that is, you're going to be able to, now you still won't be able to take it twice, but you will be able to take it independently, not have to be proctored. The test from there on out will be proctored. So that next test will be on your time, and is what we're looking at. So any other questions about the test before I move into 2.2?
No.
Okay. I did, just to note, there are some of you who have not yet worked on 2.1. A couple of you have worked, or maybe 3 have worked substantially, but there are still 4 who haven't really done anything with 2.1. That was distance formula, midpoint formula, Pythagorean theorem. So it was technically due today, so it's not showing past due. But you're going to have to kind of double time it, because you're going to have 2 assignments now, 2.1 and 2.2, which I'm going to assign today. So with that said, 2.2, really what we're up to right now is kind of the preliminary stuff we need about graphing. So 2.2, what it's really getting at is just looking at what is the nature of any equation. So it does not necessarily just linear equation of 2 variables, but any kind of equation of 2 variables. And you look at a graph of that, and what are we really looking at? And I'm going to just go something simple. So this will be an equation of 2 variables. Solution to any equation of 2 variables is an ordered pair. That is, I'm looking for a combination of numbers. I can, one I put in for X, one I put in for Y, and make this a true equation. So any equation of 2 variables, you're looking at actually infinitely many solutions. There would be actually, infinitely many ordered pairs that would satisfy this. Now, at the same time, there would be infinitely many ordered pairs that do not make that equation true. And so when I look at a graph in a rectangular coordinate plane, what I'm looking at is the solution set. It's a representation of the solution set of that particular equation. And when we look at different types of equations, what we're going to notice and look at their graphs behave. That is, all linear equations of 2 variables, the graphs look like lines. Quadratic equations of 2 variables have the shape of what we call a parabola. Degree 3 equations of 2 variables have this kind of an S shape, so on and so forth. Absolute value equations of 2 variables have the shape of the letter B. And now, one of the things you'll do in this section is talk about finding X and Y intercepts. Anytime we sketch a graph, we always, any intercepts, and what we mean by that is where the graph crosses or touches x-axis and y-axis. We always want to identify all intercepts every time we sketch a graph, look at a graph. Now, any point on the x-axis is going to have a y-coordinate of 0. And likewise, any point on the y-axis is going to have an x-coordinate of 0. So to find x and y intercepts, say we're finding x and y intercepts of this. In one case, the y-intercept, I'm going to let x be 0. So in for x, you substitute 0, and this one's fairly simple, and solve for y. So in this case, y is going to end up being 2. And I would say that is the y-intercept. So likewise for x-intercepts, let y be 0. And so in this case, x would have to be 3. Now, certainly other equations may have multiple intercepts on each axis. That very easily happen. In this case, there would be one y-intercept and one x-intercept. And so I can plot the points. Here would be 0, 2. And for a linear equation of two variables, which means the highest power on any variable is 1. And it's so linear equation, it's the word line is right in the word linear. Try to get that as straight as I can. We get the graph of a line. Now, next time on Wednesday, it's all going to be about linear equations of two variables and everything and all the tools we need to deal with graphing lines. Today is more of a general, just equations of two variables. All right, so given any equation, we always want to be able to find x and y intercepts, and the process never changes. And to find x-intercept, let y be 0, solve for x, and then flip that for y-intercepts, let x be 0, solve for y. All right, so that is intercepts. And the next thing in this section we want to deal with is symmetry. All right. So when we look at graphs, we want to analyze, is there any kind of symmetry? And that just to simply put, something that will take a graph and we can put in some cases, what we call a line of symmetry, a line either horizontal or vertical. Sometimes it could even be slanted, that cuts the graph in half, where that is, I see the mirror image on each side. In this case, in this section, we're going to focus on 3 types of symmetry: about the x-axis, about the y-axis. So in that case, we are looking at a line of symmetry, but we're also going to, this would not be a line, but we're going to look about one more thing in symmetry, and that is about the origin. That is 0, 0. So it's 1 point. So these are going to be the 3 types of symmetry we're going to look at. We're going to tackle this 2 different ways. One, just visually looking at a graph. And then 2, just given an equation without its graph. And I may have no idea what that graph looks like, but having an algebraic test to determine if there is symmetry. So kind of looking at x-axis. All right. So I'm going to just draw a graph that would have symmetry about the x-axis. So as much as my artistic ability will let me, what I'm trying to draw here and what I'm wanting, it's not perfect, but I look at above the x-axis here. If I'm symmetrical, I will see its mirrored image on the other side of the x-axis, in this case below the x-axis, like such. Now, in general, any point, if this graph is symmetrical about the x-axis, I can pick any point, x, y, and for that point, if I have perfect symmetry, then I can drop perpendicularly to the x-axis, which would be the line of symmetry. So hit it perpendicularly. And, there would be a certain distance from that point to the x-axis. We'll call that distance d sub 1. Then, again, this would be perpendicular. keep on going until I hit the graph again. And of course, there would be a distance here. Now, if I have perfect symmetry, those distances are the same. So this has to happen for any point here along this side. I can find a mirrored image point on the other side at that same distance going perpendicularly through the x-axis. Now, what would this point look like? I'll give you a hint here. Since I didn't move left or right, I just dropped straight down. This point would also have the same x coordinate. What would the y coordinate be? I'm sorry?
Negative y.
Yep, the opposite of y. So whatever this y coordinate is, its mirrored image point would be opposite in sign. That is it. And if that happens for any point xy that I pick, and I can always find its mirrored image point in this fashion, then I have symmetry about the x-axis. Okay. So then going to look at symmetry about the y-axis. I'm going to draw an example, something that looks symmetrical about the y-axis. It's going to be the same kind of argument. I can pick a point here and I can find a mirrored image point on the other side of the y-axis. So move. And those distances are the same. This time it's mirrored image point. The y coordinate would be the same, but the x coordinate would be opposite in sign. So then the last kind of symmetry we're going to look at is going to be about the origin. So we don't have a line of symmetry, it's a single point. So something that would have symmetry about the origin might look like this. Oh, not like that. Okay, not too bad. All right, so, but I'm going to make the same kind of argument. I'm going to say pick any point here on the graph. And so I'm going to go from that point to the origin. So say that's d sub 1. Then I'm going to be able to go that same distance and strike the graph again. So d sub 1 equals d sub 2. Wouldn't say it's going, you're not going to hit a point perpendicularly, but the distances are the same. And this mirrored image point here, in this case, if you have symmetry about the origin, will be opposite of x and opposite of y in this case. So those are our three types of symmetry. Now, would it be possible for a graph to have all three simultaneously? And what would that look like? Could you visualize that in your head? Have all three types? And the short answer is yes, it is possible. What would it look like? What's the simplest one?
Would it have like a line in all four quadrants? I think.
So let's say we've got XY plane. I'm terrible at drawing these. What did I draw?
A circle.
Circle, yep.
I was like an X.
But whose center is the origin.
Okay, that makes sense.
Yep, a circle is a geometric definition of a circle is a set of points in the plane, all equidistant from a fixed point. And that fixed point is what we call the center. That same distance is called the radius of the circle. In 2.4, we're going to look at equations of circles. All right, so that would be one example. Here's another one. So you're going to have some homework problems here in 2.2 where you're just doing this visually. It gives you a graph. So I'm going to draw a quick sketch of a graph. Oh, as best I can. And you're going to have at least a couple points labeled. So let's say that point right there is 1, 0, and this point is -1, 0. All right. This one, I would also argue, if I were just looking at it visually, has all three types of symmetry. Certainly, it looks like we're symmetrical to the y-axis. It looks like where I see the mirrored image on both sides of the x-axis. And then I can pick a point here, go through, and I find a mirrored image point here. For any point I pick, I can go through the origin and find its mirrored image point. So that would be another graph that would have all three types of symmetry. One more. What do you think about this one? Does it have any of the three?
No.
No, it doesn't. So, you know, when I would just go through the three, okay, y-axis, nope, I would need to see again the mirrored image. And I don't see, definitely do not see a mirrored image of, you know, either going either direction. If I take this part on this side of the y-axis, I don't see its mirrored image over here, vice versa. I don't see anything below the x-axis at all, so I certainly don't have a mirrored image across there. And if I try to go through the origin, again, same problem. I don't see any graph. You know, if I pick a point here in quad 2, I don't see its mirrored image point should, if it have symmetry through the origin, should be down in quadrant 4. And I don't have any part of the graph down here. So that would be none of the three. Now, just something in general about graphs. These arrows that I put on here are actually very important. When I put those arrows in on a graph, what I am now saying is the graph continues forever and ever in that same fashion without change. Meaning there's nowhere where the graph's going to turn back, or, you know, in this case, it's going to be just going up, up, and up, and out forever. What's going on here? Does anyone know the word? It's a big word, begins with the letter A.
Big word, letter A.
Hold on.
I don't know.
Have you ever heard or dealt with something called asymptotes?
I was about to say that.
Okay.
I got the first. No, I got the first part.
So asymptote. Now we'll be dealing with this extensively later on in the semester. But when I put that arrow here, but I don't show it because you always find all intercepts. So I don't show it crossing the x-axis or touching the x-axis at any point, but I show that getting near the x-axis. I'm indicating in that case, the x-axis for this graph is what we call an asymptote, at least into the negative direction, which means it gets what? Closer and closer and closer to infinity, but never actually hits the x-axis. This graph that I just drew here is an example of what we're going to call an exponential function. Again, that's at the end, that's in April. That's at the end of the semester. Okay, so that's looking at it visually. What about algebraically? So let's say I take an equation. Y squared equals x plus 9. Now you may know in this case, and you may not, this is going to be what I'll call sideways parabola. Whose vertex is -9, 0. Has y-intercepts of -3 and 3. but you may not know that. And how would I be able to determine this algebraically? So given any kind of equation of two variables, what does a test look like to test for these three types of symmetry? And so that's what I'm after now. I want to talk about, does it have any of the three types of symmetry? I want to test algebraically. Okay, so it goes back to those three graphs I initially drew, just talking about what it means to be symmetric about the three different things. For the x-axis, if you have symmetry about the x-axis, then given any point xy, its mirrored image point has to be x opposite of y. So the test for symmetry about the x-axis algebraically is to take the equation, anywhere I see y, I put in its place the opposite of y. And watch, where you're putting it. So like y is here in this equation, it's y squared. So if I put in the opposite of y, in for y, that negative is going to be squared out. So in for y, I put negative y. So the base is now negative y. Now, if I have symmetry, I'm going to be able to, using correct rules of algebra, manipulate this and get it back to what the original equation. So this one's fairly simple. It's just, I can square out that negative. So I now have y squared equals x plus 9, which is what I originally started with, which means, yes, I have symmetry about the x-axis. Y-axis is going to then be just like we did for x-axis, but not opposite of y. If I have symmetry about the y-axis, I'm going to be able to put in the opposite of x and then manipulate it back to my original equation. So if I do that, in for x, I put the opposite of x. But the issue here is, I'm looking, okay, I need to make that positive x. So I can think about, okay, what could I do algebraically to try to get this to look like what I originally started with? The only thing I could really do is multiply both sides by -1. I could do that. Note the difference here. I'm multiplying this side by -1, but the negative is not part of the base here. So it's not going to get squared out. -1 times x is x, but then I'm going to have to multiply that term by -1 as well, and it gives me -9. And so, no, I cannot manipulate this to look like what I originally started with. So I don't have symmetry about the y-axis. The origin is put in opposite of y and opposite of x. Well, that negative will square out, but I'm right back to where I was with the y-axis. I can't get rid of I can get rid of this negative, but I'm going to make both of these negative. So I cannot manipulate it back to what I originally started with. So no, I don't have symmetry about the origin. It'll also, you have problems when you're doing this algebraically. It'll say find the intercepts. So remember, if I go to find intercepts, say I want x-intercept, let y be 0. Solve for x. Well, that's 0, and I can take the 9 over there, and boom, I get this. Now, when you are working the problems on my math lab, pay particular attention once you get your intercepts and you're going to input them in to the answer fields, that read in blue, because there's two ways it could be asked. It could say, put your intercepts in as ordered pairs, which in this case means x is -9 when y is 0. Or it could just say type in an integer or a rational number or a decimal rounded to whatever place value, in which case you're just putting in the number where it crosses the axis, not actually listing it as an ordered pair. So make sure you read, and you're going to see in that homework set, some problems will ask as ordered pairs, some will not. Y-intercept or intercepts, let x be 0. So in this case, you have y squared equals 9, taking square root of both sides, y equals plus or minus 3. And if it asks for ordered pairs, in this case, there are actually 2 ordered pairs, you can go to the toolbar, use the plus minus key. And that's not what I wanted to say. X would be 0. But you can kind of write it as 1 ordered pair, but to put the plus or minus 3, which indicates, again, 2 ordered pairs, 0, 3, and 0, negative 3. Okay. Time is 10:19, so about 10 minutes. All right, we'll look at one more equation. Let's say we looked at y equals x squared minus 4 divided by 2x. So looking at, do we have any of the types of symmetry? We'll put x-axis, y-axis, origin. All right, so for the x-axis, we put in the opposite of y wherever I see it. So now I've got opposite of y equals x squared minus 4 all over 2x. And then I ask myself, look and see, can I manipulate that to look like what I originally started with? And the answer here is no. I could multiply both sides by -1, which would give me y here. But now I've got a negative over there. And so, no, I do not have symmetry about the x-axis. Y-axis, I put in the opposite of x everywhere I see x. So I would have y equals now opposite of x all squared minus 4. And then 2 times now negative x. And that negative up top will square out. And that's going to give me x squared minus 4. But in the bottom, I've got negative 2x. I could multiply again both sides by -1, which would get rid of that negative here. But that's not what I originally started with, because I've got this negative y. So I can't get rid of it. And again, the answer here is no. So when I test for the origin, I put in the opposite of x and the opposite of y. Now, in this case, again, that negative squares out. And I could multiply both sides. And so I'm going to go ahead and do this in 2 steps. So I've got x squared minus 4 up top. I've got negative 2x here. I could multiply both sides by -1, which would give me y equals x squared minus 4 over 2x, which is what I originally started with. So I was able to put in opposite of x and opposite of y and get back to what I originally started with. So yes, this graph would have symmetry to the origin. Now, as far as intercepts go, check for x intercept or intercepts. Let y be 0 and solve for x. Okay. So in this case, a fraction is 0 when the numerator is 0. So, or you could think of it as multiply both sides by 2x, which would clear out here, and anything times 0 is 0. So all I really need to figure out is what would make the top equal to 0. So 4 equals x squared, or plus or minus 2 is x. So there are two x-intercepts, 2, 0 and negative 2, 0. Y-intercept, or intercepts, let x be 0. So this one's going to be a little easier. Now that's going to end up giving me negative 4 over 0. And what is that?
It's not just -4.
Nope.
Undefined.
Undefined. It's nothing. All right. So what this tells me is, now it would be -4 if it were -4, say, over 1. But this is not defined as a real number. You cannot divide 0 into -4 and make that division work. And since that's undefined, there are no y-intercepts. So, which is just as important to know, okay, this graph would not cross the y-axis at all at any point. So that is the fly-by-night version of 2.2. While we're on this subject here real quick, and this is something you will deal with in calculus. So 0 up top, let's say I have 0 over 4, that's 0. And we just discussed, if it's 0 is in the bottom, it's not a real number. It is undefined. Now, here's something to think about. Way back when, you were also taught, if you have a number over itself, that's what?
1.
That's 1. Okay. So if 0 up top gives me 0, and 0 in the bottom is undefined, and a number over itself is 1, what in the wide world of sports is that?
What?
You can make an argument for 1. You can make an argument that it is undefined, and you can make an argument that it is what? 0. It's like all three things simultaneously, but it's not. Right. So if I had to, what's a simple way to figure out what this thing is? And again, this is something you will actually deal with at the beginning of a calculus course, dealing, maybe not so much at the beginning. You will learn about limits at the beginning of a calculus course. And then later on, once you have derivatives, you'll learn to take limits of this situation, 0 over 0. So what is it? So backing up to this, what makes, if I had to explain to somebody why 0 in the top is 0, well, a fraction is division. 4 divides into 0. Can I make the division work? Well, yeah, 4 divides into 0, 0 times remainder of 0. So the answer is 0. This is undefined because if I try to divide 0 into 4, I can't do it. I can't pick it. There's no number I can pick here to make this division work. So we just say it's undefined. So I turn to this one. Now, 4 divided into 4 goes 1 time. Can I put a 1 here and make this work? 0 times 1 is what? 0?
Mm-hmm.
Yeah.
Yeah, it works. But could I put a 2 here?
Yeah.
Could I put a 3 here?
Yeah.
Okay, I can put any number I want. So what this is called, it's not undefined, it's not 0, it's not 1. It is referred to as an indeterminate. I can't determine what it is. Again, you will see that in a calculus course. Once you have derivatives, you'll take limits And I'm not going to get into what that means right this second, but you come up with 0/0, and then there's still a way to figure out what the limit is using what's called L'Hopital's rule. But anyway. All right, so I'm assigning, I'll put,
The new office, Dallas Pickett, Matt DeHall, Hope Mason, Beard Smeltup, Cameron Starcher. Please come to the new office.
okay. I'm going to assign 2.2 homework, put the due date as Wednesday or excuse me, Thursday. And I'll also put the videos if you want to watch those associated with 2.2.
Okay.
3 points, and good luck tomorrow. And if you think of any last minute questions on the test before tomorrow, you can shoot me an email, and I'll send a video link out later today for today's session. All right. See you guys on Thursday.
Okay, thank you.